Hello and welcome. This is going to be a video on the Solow model with population growth. In this, we're going to review the Solow with population growth added into it. We're going to derive the new law of motion of capital. That's the equation that describes how capital is accumulated in this economy. We're going to find the new steady state level of per worker capital and per worker output, as well as solve for aggregate output Y, capital K, consumption, investment savings, and then end up with a discussion of steady state levels versus balanced growth paths. The focus of this video is going to be to kind of on the nitty-gritty details of how to reach the analytical solution of the model, which is kind of like the boring, mundane stuff that professors usually skip over for us to cover in tutorial section. Because I hope to cover so much of the boring stuff, I'm going to leave kind of the intuition, that sort of explanation of the model to your professor or the textbook or a later video. If you want to skip ahead or check out those other topics, be sure to check out the video description, and I'll have links to either allow you to skip ahead or find those other things. Overall, in this model, in this video, we're going to set up the model, discuss some of the notation, find the law of motion of capital, calculate these steady states. We're going to review the diagram, talk about time series, and then end with a summary. Okay, let's get started. So in terms of setup, our production function here is the typical production function taking the form of a Cobb-Douglas production function with constant returns to scale. The constant returns to scale is required for this Solow model to work. Our goods market just reflects the fact that income is going to equal all the ways that people could spend their money. So Y reflects income, C reflects consumption, and I reflects investment. Basically, you make a certain amount of money, Y, and you have to put it to use in some way. And in this simple model, in this simple economy, people have two things to do. They could either consume or they could save some of that money with investment. We're going to have this value S here, which is a constant number standing in for the investment, the savings rate. So S is the savings rate. Given that you have, you make a certain amount of money, that money could go to one of two places. So it could go to investment, and the portion of your income that goes to investment is defined by the savings rate. So savings rate is like, I think 20%, 30%, some number like that. And then the rest of the money goes to consumption. The rest of your income, so 1 minus S times your income is going to go to consumption. Also, the model deals with per capita levels. Sometimes I refer to it as per worker levels. So what do we mean by per capita or per worker? So we usually notationally designate it by a lowercase k here. So per worker capital is just the quantity of capital in the economy divided by the number of workers. So K divided by L. So per capita output here is just the total production in the economy divided by the number of workers. We sometimes show that notationally as this F of lowercase k, because if you take the total production function, this Y here, production, is just a function of capital and labor. And if you then divide it by the number of workers, you could also write it equivalently here. So it's F of lowercase k comma 1, because L divided by L is just 1. So usually notationally we show this per capita output as F of lowercase k or Y over L. For that to work, we need that constant returns to scale. And then similarly, per worker investment and per worker consumption is just total investment divided by the quantity of labor, or for per worker consumption, it's just total consumption divided by the number of workers. This model also kind of complicates things a little bit more by having a rule that defines the accumulation of capital. So basically, capital changes through time. So that's one reason why we added that little sub-T subscript. Capital grows with investment. So people make a certain amount of money. They take a portion of that money and move it into investment, and that investment becomes new capital. So capital can grow through this I term, investment, which is kind of ruled by the amount of new capital created. It's going to be defined by the savings rate and defined by what aggregate output is going to be. And then also we have a part of capital is going to be destroyed each period. That's going to be defined by depreciation, which we'll get to a bit later. The other thing we're complicating things with is we add population growth. So where before in the simple Solow model we had L, the labor supply, was some constant number. Sometimes it was noted as L bar to indicate that it's a constant level. We now have labor, moving through time, changing through time, and it's going to grow at a rate of n here. Sometimes you also see growth rates noted by G sub L to show that's the growth rate of L, labor supply, so it grows at n. And another way to write that equivalently is that the growth rate here, n, is L dot over L, which we'll get to in a minute. So when you see something with a little dot above it, so you'll see L dot, you'll see K dot. That's basically the change in labor divided by the change in time. So it's kind of like how this L dot is like how labor changes given a unit of time. And so how labor changes given a unit of time depends on how much labor is there to kind of work with, and then times that by the growth rate. And then notationally, a few other things to look out for are our stars again, like lowercase k star, y star. These are going to indicate steady state levels as well. Also, there's quite a few assumptions that kind of describe what the production function should look like, as well as exactly how the good markets clear. And I'm going to kind of gloss over those for ease of explaining all of this. Okay, so let's get started. First off, by finding the law of motion of capital. Law of motion of capital is maybe perhaps kind of a scary term for you. You often see the law of motion of capital referred to in textbooks as kind of the capital accumulation equation. So it's an equation that's going to describe how per worker capital changes through time. So it's basically, our goal is to find this. Our goal is to find K dot, the change in capital given the change in time. So how do we find that? I'm going to focus on continuous time because I think it's a little bit easier to work with. I have the kind of solution I worked out for discrete time over here. So yeah, our goal is to find how capital evolves through time. So let's start off with what per worker capital looks like. That's just lowercase k is equal to capital K divided by L. So if we log this, we get the following. We get the log of capital is equal to the log of per worker capital is equal to the log of total capital minus the natural log of population. So we could then, in order to get our start getting our dealing with how per worker capital evolves through time, we could take the total differential of all of this. So if you remember calculus, if you take the log of something, you're going to get how that changes through time. So if you take the total differential with respect to time of something, like ln k here, you get how that thing changes through time times 1 over k. That's just a property of natural logs. So by taking the total differential of this equation here with respect to time, we get this equation right here. So this is how per worker capital changes through time times 1 over per worker capital is equal to, and then the rest. So the next step here is just kind of a notational twist, right? So the change in per worker capital divided by the change in time, that's equivalent to K dot. That's just how capital evolves through time. I misspelled notationally. Nope, I spelled it right. So rewriting this equation here, just with our new notation, we can see that K dot divided by K, so that's the growth rate of per worker capital, is equal to the growth rate of capital minus the growth rate of population. So this stuff right here, so the growth rate of the population, we're given by assumption that that's just equal to n. So the labor force grows at rate n. So that's this equation, right? And then K dot, we already discussed in our assumption section how that grows through time, right? So what is K dot? What is the change in capital given the change in time going to be equal to? K dot increases with investment, so that's savings times aggregate output, and then a part of capital is destroyed each period defined by the depreciation rate. So it increases by this and then minus the depreciation rate. So this K dot, so just the change in capital, is equal to investment minus how much is destroyed, depreciation. So plugging those in, so our value for K dot, and plugging in the growth rate of labor, we get the following. We get the percentage change in capital is equal to this stuff divided by K, because that's just standing here, minus the growth rate of labor supply. And our goal, right, is lowercase k dot. It's per worker. It's how does per worker capital change. So in order to simplify things to get just by itself, we times both sides by per worker capital. So this stuff right here, so savings times total output times per worker capital is this term right here. We see that this capital term cancels out, and then lowercase k dot up here times the depreciation times capital, right? These things to just kind of cancel out, leaving minus delta capital. Basically, things simplify to the following. K dot, the change in capital, is equal to the savings rate times per worker output minus delta plus the growth rate of the population times per worker capital. You could also follow similar steps to get a similar equation dealing with discrete time, and you'll get the change in per worker capital is approximately equal to, once again, per worker investment minus this kind of depreciation, this what we call like the break-even amount of investment required to keep capital constant. So what's this term right here again? Well, remember before we had it times delta capital. That's how much capital is destroyed each period, delta capital. So the depreciation rate times how much capital there is. So if you just wanted to keep the capital stock constant, each period you need to add to the capital stock delta times the existing capital stock. That's like the break-even amount of capital. But now introducing population growth, in order to keep per worker capital constant, in addition to creating enough capital to cover depreciation, you now need to also create enough capital to give to all those new workers in the economy. So given population growth, there's new people, there's new laborers working, and in order to keep this per worker capital level constant, those new workers need some capital for themselves, right? So this new break-even investment that's required to keep per worker capital constant needs to take into account depreciation as well as the population growth. So this is kind of a key equation here. The change in per worker capital is equal to the per worker investment rate minus the depreciation rate plus the growth rate of the population times per worker capital. This is what we call the law of motion of capital, or I think it's sometimes called like the capital accumulation equation, something like that. Okay, let's move on. Next up, we're going to find the steady state level of capital. Steady state level of capital. I'm going to do this in close to continuous time. I have the steps over here to do it in discrete time if you want to see. It kind of gets a little clumsy looking, so keep with the continuous time approach because things look kind of cleaner that way. So how do we find the steady state level of capital? Well, first off, we're going to find that it's not a steady state. It's actually something that grows. But in general, if there was a steady state, how would you find it? Well, you would take the capital accumulation equation, so the equation that defines how capital changes through time. Remember, that's just investment minus depreciation. That's how this capital K, the total capital stock, changes. And to find the steady state, well, steady state's defined as a level of capital such that if the capital level were that, actually I wrote it right here, didn't I? Steady state level of capital is a level of capital K star that if the current capital level were this level, K star, then the change in capital would be equal to 0. It wouldn't grow. It's a steady state. So this is just kind of like the, tautological definition of what a steady state is. So what we basically do is we take this equation that describes how capital changes through time, and we set these terms to over here equal to 0, because that's the very definition of a steady state. So that's this first step right here. We say that the change in capital is equal to 0, which is equal to our aggregate total capital accumulation equation. So the other thing is this y here, output, is defined by the production function. So we're going to look to see what the production function is, which we have is A stands in for total factor productivity times capital, which changes through time, raised to the alpha, times labor supply raised to 1 minus alpha. This is just our Cobb-Douglas production function. So note that capital is a function of time normally. However, by defining it as a steady state level, we're calling it this K star. And then also labor, we were told, changes through time, right? Because it grows at rate n. So plugging all that in, we have 0, the change in capital is equal to the savings rate times output y minus delta minus the current capital stock. If you solve through that, you just kind of churn out the nitty-gritty algebra required, you find that the steady state level of capital, so K star, is equal to all of this, the savings rate times total factor productivity divided by the depreciation rate, all raised to 1 minus alpha, 1 over 1 minus alpha, times population growth. So a bunch of these things are constant, right? The savings rate's constant, we assume. Total factor productivity in this model's constant, we assume. Depreciation rate's constant, we assume, and then this alpha, which is, I think, capital share of output, is also constant. However, so all of these things are constant, which means the steady state level, if the steady state level of capital were a function of just these things, as it is in the simple model, the steady state level of capital would be a constant. But it's also a function of the labor supply, so the quantity of labor. And that's something that changes through time. Since labor grows at rate n, we know that this capital stock is going to grow at rate n. So although we tried to find the steady state level of aggregate capital, total capital in the economy, we found that there's no real steady state. It's actually kind of something that's growing through time. So it's a function of this quantity right here, which are all constant, times labor, which grows at rate n. So this capital stock is actually going to grow at rate n. Okay, let's move on to the next part. We're now going to try to find the steady state level of capital per worker. So that's per capita capital. That's the lowercase k. We just found the steady state level of aggregate capital in the economy, and we found that it's not a steady state at all. It's something that grows. Now we're going to find the steady state level of per worker capital, and we're going to find it's a legitimate, it's a steady state. It goes to one level. So once again, how do you find the steady state level of something? Well, you set up the equation that defines how it changes through time, which above we found this. So per worker capital changes through time. It's equal to per worker investment minus depreciation plus population growth times the existing stock of capital per worker. So to find the steady state level, we need to set that k dot equal to 0. So this is going to be equal to 0. And then we're going to solve for k star. So we could plug something in for this lowercase y, because lowercase y is just per worker output, and per worker output is just equal to that f of k, which is, when you solve through it, it's total factor of productivity times per worker capital. Should be raised to the alpha. And then if we just follow the steps, which I went through in nitty-gritty detail over here, we find that the steady state level of per worker capital is going to be equal to this equation right here. So it's going to be equal to the savings rate times technology, our total factor of productivity, divided by the population growth plus depreciation, and all of that raised to 1 over 1 minus alpha. I guess in this continuous time stuff, I skipped over those steps. So what we did is we plugged in the per worker output equation right here, A times K raised to the alpha. We plugged that into our capital accumulation equation. And then from here, we have a K star here, and we have a K star here. So the next step is we just solved for K star, which ends up with this equation. So this is our steady state level of per worker capital, and it's a total steady state. It's equal to these things. So next we're going to find the steady state level of output. So aggregate output is y sub t. Remember, that's equivalent to something like real GDP. And then it's equal to the production function here. So A, total factor productivity, times the capital stock raised to alpha, times the quantity of labor raised to 1 minus alpha. So a steady state level of output is a level such that if that's the current level, if the steady state level is the current level, y star is the current level, then it will stay at that level for all time. That's what we're saying right here. We're going to find when we solve through this that it's not going to be a steady state at all. It's going to be a balanced growth path, but that's kind of how we set up how to find it. So we're going to say that our quantity y star here is going to be equal to, so our y star is a function of these things here. Well, we know that L is not constant. It grows, right? It grows at rate n. And then also our capital stock here, we found out it wasn't constant. It grew at rate n as well. But we did have an equation that described the aggregate capital stock. We found that above. And then we are kind of just by assumption, because population grows at rate n, we also have an equation that we could plug in for the labor supply. So we can actually find what the balanced growth path of output, or sorry, the growth rate of total output is going to be by plugging in our values that we know for capital and labor. So how do we do that? Well, above we found K star. Remember, K star was equal to this stuff right here. So we're plugging that into K star, and then we'll take care of labor in a second. So solving through this, we get down to this equation. We get that output is going to be equal to total factor productivity raised to this exponent times the savings rate divided by delta raised to this exponent times the labor supply. So these things right here are all constant, right? Because total factor productivity, savings, depreciation are all assumed to be constant, perhaps unrealistically so, but they're assumed to be constant, times labor, which grows through time. How does labor grow through time? Well, once again, it grows at rate n. So at any time L sub t, it's equal to the base level of labor, like our starting point, times 1 plus n raised to the t. I think it's a little bit easier to think of it over here in continuous time. So how does output grow in the steady state? If our per worker capital level was at the steady state, so it appears that per worker, per capita capital is constant, it's at the steady state, what is output going to look like? Well, output is going to just continue to grow at the rate that the population grows. And then the last thing we're going to want to solve for, find the steady state level is output per worker. So output per worker is that lowercase y. Lowercase y is equal to aggregate output divided by the number of workers. And then when we solve for the production function, the per worker production function, it gives us a result that it's equal to A, technology, total factor productivity, times per worker capital raised to the alpha. So if we want to find the steady state level of per worker output, all we have to do is plug in the steady state level of per worker capital into this equation here. The per worker capital has a steady state, like just a fixed constant level, and it's just a function of capital. So we're going to plug in what we have for the steady state level of capital into the rest of this equation, and that's going to be our steady state level of per worker output. So first things are just kind of set up. So y star, lowercase y star, the steady state level of per worker output, is equal to total factor productivity times the steady state level of capital, all raised to the alpha. So it's equal to this equation right here. The next step is kind of simplifying like terms, or combining like terms, right? So we got A over here and A over here, so we need to combine them together. All of this simplifies down to the steady state level per worker output with population growth is going to be equal to this equation for technology times savings over the population growth plus delta, all raised to this. Cool. So let's summarize everything. I kind of showed you the steps that you need to take to find those values, and you could conceivably, if this is the model you're working with, it's just a model with population growth, savings rates, depreciation, and constant technology. You could kind of just plug in, say you were given values for savings or population growth or delta. You actually just plug in those values, and it'll give you the steady state level of output. To summarize everything that we've gone over today, I'll review it below. So all the things that we solved for were K star, per worker capital, Y star, lowercase y star, per worker output. And indirectly we solved for savings per worker. And we also indirectly solved for capital, we solved for consumption per worker. And then we also solved for aggregate capital, we solved for total outputs, and then indirectly we solved for the investment and consumption.